Module 5, headline. Module 5, different anchorage system and design of end block by latest IS codes. This different anchorage system, it is available in module 1 notes. Even I have discussed this in module 1 students. I will be not repeating once again on this same topic. I will be discussing the second part of the model design of end block by latest IS codes. Okay. So before understanding what is the meaning of end block, you need to understand few basic things. Okay. Few basic things, that is anchorage zone stresses. Okay. Anchorage zone stresses. Then you need to understand about the bursting force. Bursting force I'll be discussing in detail in this class. Bursting force, then uh, you need to remember few formulae for designing the end block. Okay, I'll explain what is the meaning of end block. Okay. Now let us see what is the meaning of anchorage zone. What is the meaning of anchorage zone? See, we all know that in case of post-tensioned elements, in case of post-tensioned beam elements, what will be done here? In case of post-tension beam element, the pre-stressing wire will be stretched. Okay, pre-stressing wire will be stretched and anchored at the ends by using some anchoring devices with the help of anchoring plate. Okay, of rectangular section, sometimes the circular sectioned plate will also be provided. Okay, this is how we do pre-stressing in post-tensioned concrete elements. Okay. Now, when the wire is stretched to a required degree of pre-stressing force P, okay, and is released and is anchored at the ends, Here you can see initially what we'll do, we'll stretch the wire, and after stretching we will anchor the wire by using some anchoring devices and anchoring plate. When you stretch the wire, then what will happen? There will be this wire will tend to reduce its length. Okay, it will undergo the elastic contraction. Okay, it will try to contract elastically. Okay, that is why the pre-stressing force P will be induced. Compressive pre-stressing force P will be induced in the wire, pre-stressing wire. In this case, what happens? When you compare the cross section of the pre-stressing wire to that of cross section of the beam, okay, let me write here. When you compare the cross section of the pre-stressing wire to that of cross section of the beam, cross section of the pre-stressing wire is very less compared to cross section of the beam. Therefore, whatever the pre-stressors which will be which we have to induce on the cross section of the beam, they will not be transferred to entire cross section of the beam. They will not be transferred to entire cross section of the beam. Okay, what happens? We will get a regular longitudinal stresses. Okay, initially the stress distribution will be to a lower area like this. like this, the longitudinal stresses will be generated in the member. Okay, and this longitudinal stress distribution is due to the compressive force which is carried by this tendon. Okay, the compressive force carried by this tendon. This tendon will try to contract. Okay, elastically. Okay, when it's stretched and anchored, what happens? That tendon will try to contract elastically. Because of that, there will be longitudinal stresses induced in the member. Okay, there will be longitudinal stresses induced in the member. Therefore, the zone between the end of the beam, okay, the zone between the end of the beam and the section where only longitudinal stresses exist, okay, the section where the only longitudinal stresses exist is generally referred to as the anchorage zone or the end block. This portion, whatever I have written, it is called as end block. Okay. And one more important thing, when this wire try to contract elastically, okay, means when we apply the compressive force on one direction, then in the transverse direction, perpendicular to the direction of applied compressive force, what will be the change in the dimension of the beam? There will be tensile force induced in the transverse direction. Okay, when you apply compressive force in the longitudinal direction, then in the transverse direction there will be tensile force that is induced in the transverse direction. Whatever this tensile force is called as, whatever this tensile force or the force which is induced in the transverse direction is called as bursting force. It is called as bursting force. I hope you are following the lecture. There will be two kinds of stresses induced due to the compressive force which is carried by the tendon. Okay, one is longitudinal stresses, and one more is transverse stresses. Okay, which are tensile in nature. Transverse stresses which are tensile in nature. Because of this transverse stresses, the transverse force, which whatever it is generated, that force is called as bursting force. Okay. Therefore, the concrete member, the pre-stressed concrete member is to be designed to resist this bursting force or tensile stresses which is induced in the transverse direction. Okay. To prevent this tensile, the bursting force, what we'll do, we'll provide the transverse reinforcement. Okay, we'll provide transverse reinforcement. It means we will provide some steel mesh at this particular zone because there will be lot of stresses induced at this particular zone. To withstand all these stresses, transverse stresses or tensile stresses, we will provide this end block. We will design this end block. This portion, whatever we are designing, it is called as design of end block. Okay. When the compressive force is induced into the concrete member, very simple. When the compressive force induced in the concrete member, in the transverse direction, in the vertical direction, tensile force will be induced, means tensile stresses will be induced. Okay, to resist these tensile forces, we have to, this concrete is very good in compression but weak in tension. Okay, to strengthen the concrete for tension, what is the alternative? We have to provide the reinforcement. Means we will be providing steel mesh, vertical steel meshes in this particular zone. So designing of this steel at this block, okay, at this anchorage zone block is called as design of end block. It's called a design of end block. Okay. And there are certain guidelines which we have to follow for design of end block. Let us say And there are some parameters which will come during the design of the end block. Okay, during the design of the end block. The first thing what we have to consider for design of the end block is bursting force. Okay, by considering this bursting force only, we will design the reinforcement or we will design the steel mesh. Okay, now let us see how to find this bursting force. Okay, let us see how to find this bursting force. Bursting force is represented by FBST. Okay, bursting force is represented by FBST, and it is determined using the formula which is given in the code book. I think in page number 36 it is available. Let me see it. Yeah, here we have the formula for bursting force. FBST by PK is equal to FBST by PK is equal to 0.32 minus 0.3 minus 0.3 into YP naught by Y naught into YP naught by Y naught is the formula. Okay, where FBST is the bursting tensile force. Okay, bursting tensile force, and PK is the load in the tendon. Okay, PK is the load in the tendon, that pre-stressing force. Okay, pre-stressing force. And YP naught and Y naught are the side of the loaded area and side of the end block. Okay, Y naught is nothing but side of the end block, means this length. Okay, this length. This depth of the plate is there, no? This is taken as 2y naught. Okay, why it is taken as 2y naught, I will explain you in the future classes. Okay, maybe in tomorrow's class I will tell you why this is represented by 2y naught. Okay, this depth of the plate is taken as y naught, nothing but 2y naught, and one more parameter is there, yp naught, side of the loaded area. Yp naught calculation, this yp naught is there, no? It is sorry, this yp naught is nothing but the depth of the plate. Sorry, it is 2 yp naught. 2 yp naught, side of the loaded area. Okay, so whatever the depth of the plate is, it is there, that we consider it as yp naught. Okay, whatever the depth of the plate it is there, we will consider it as yp naught, and y naught is nothing but side of the end block. Y naught is nothing but side of the end block. See, yp naught is nothing but side of the loaded area. Side of the loaded area means, I'll repeat. So here there will be anchorage plate. Okay, side of the loaded area means if you provide anchorage plate here, through this anchorage plate there will be distribution of the stresses to the beam. Side of the loaded area means this side, this length. Okay, this length is nothing but yp naught. Yp naught. Okay, instead of considering simply yp naught, we will consider it as 2 yp naught. We will denote it as 2 yp naught. The reason I will tell you in the next class. Okay, then second thing is y naught is side of the end block. Side of the end block means this one. Here also, instead of simply denoting it as by y naught, we will denote it by 2y naught. Okay, I'll tell you why it is taken as 2y naught in the next class. So this is called as size of the or side of the end block. Okay, so for this portion we are designing the reinforcement, no, for this portion it is called as end block. Okay, it is denoted by 2y0. Okay, so yp is nothing but depth of the plate. This much you remember. Y0 means this side of the end block, and calculation of this this y0, no, it is calculated in two ways and least value is taken from both the calculation. Okay, and it is also called as prism. This portion is there, no? This portion is called as prism. It is also called as prism. Okay, size of the prism is represented by this 2y0 by 2y0. Okay, it is represented by 2y0 by 2y0. Okay, and calculation of this y0, no, it is done in two ways. Let us see size of the prism. How the size of the prism is decided. Okay, first calculation is 2y0 is equal to size of the prism is the length of the prism, nothing but 2y0. This 2y0 length is calculated in two ways. One is 2 times y1. 2 times y1. Y1 is nothing but distance of the nearest extreme fiber from the tendon. This is called as y1. Okay, I'll repeat. Y1 is distance of nearest extreme fiber from the tendon. Okay, is called as y1. While solving the problems, you will understand in clear way. This much you remember. Y1 is nothing but distance of the extreme fiber from the tendon is called as y1. Okay, so this is the one way of calculating the size of the prism. Second one is 2y0, the length size of the prism, nothing but is taken as width of beam. Width of beam P. If it is a T beam or I beam, we will consider BW, width of web. For T beam or I beam. Okay. So we will calculate in two ways, whichever the least value from these two calculations, no, that least value we will consider it as the value of 2y0, that is size of the prism. Okay, this is how we calculate the size of the prism. Okay, which is required for calculation of this bursting force. Okay, if you know the bursting force, you can calculate the area of steel. Okay, you can calculate the area of steel. And to calculate area of steel, we have the formula. Area of steel is given as FBST, bursting force, divided by 0.87 Fi. Using this formula, we will calculate the area of steel. And if you come to know about the total area of the steel required, you can calculate, you can judge what is the diameter of the bar to be provided and number of bars to be provided. Okay. After knowing the diameter of the bars and number of bars, you can sketch the reinforcement details at the end block. Okay. Sometimes in the question, he will also ask you to find the tensile stress in the vertical direction. Okay, as I said, no, there will be tensile force or tensile stresses induced in the vertical direction due to compressive force in the horizontal direction. The magnitude of those tensile stresses is calculated by the formula Fc into 0.98 minus 0.825 into Yp naught divided by Y naught. This you need to remember. This formula you need to remember, students. Where Fc is the compressive stress. Fc is compressive stress. FC is the compressive stress, which is calculated as the pre-stressing force divided by area of prism, not area of cable, students. Very important. This is area of prism. Area of prism. How we calculate the area of prism? 2y0 into 2y0. 2y0 into 2y0 is will give area of prism. EP. Okay. So knowing the AP and pre-stressing force, you can calculate the FC. I already explained how to take these YP0 and Y0 values. Substituting all, you will get the tensile stresses. You will get the value of tensile stress. Okay. This is how we design the end block. Very simple steps. First, we have to get the value of YP0 and Y0. Okay. And getting the YP0 and Y0, you will get the bursting force using this equation. Knowing the bursting force, you will get the area of steel, and deciding some diameter of the steel, you can decide what is the number of steel to be provided. Okay. And one more important instruction while solving while designing the end block. Sometimes the circular plates will be given in the problem. If circular plate is given, you need to find the equivalent dimensions of a equivalent square plate, which is having the same area as that of area of the circle. Okay, if a steel plate of diameter D is given, then you need to find size of a equivalent squared plate. How to find it? You need to equate the area of square to that of area of the circle. Area of the circle is pi d square by 4, and area of square is a square. Therefore, the A is equal to root of pi d square by 4. Okay. By this, you are converting a circular plate into an square plate, which gives the same area of side A. Okay. Next, you need to proceed for the calculations. Okay. If circular plate is given in the problem. Okay. These are a few instructions with respect to the solving the design problem. And there will be in your examination there may be a theory question on transmission length. Okay, let us see what is the meaning of transmission length. Let us see what is the meaning of transmission length. For that, I will consider a beam. Okay. Beam. See here, when the pre-stressing tendon is tensioned, its elongation is accompanied by reduction in diameter. Okay, so this is the, let us assume some diameter of the pre-tension tendon. Okay, this is the original diameter of the tendon. Okay. Now, while doing pre-stressing, what we'll do, we'll stretch the tendon. When you stretch this tendon, no, what happens? There will be reduction in the diameter, correct? Like this. Okay. Now, original diameter was D1. Okay. Then after stretching, diameter reduces to D2. Diameter reduces to D2. Therefore, when the pre-stressing tendon is tensioned, its elongation Due to this elongation, there will be reduction in the diameter. Okay. After stretching, what we will do? We will release. Okay. We will release this tendon and will anchor the tendon at this by using at this zone. Okay. By using this anchoring plate. Okay. So in this case, what happens? When you release this tendon, no, the stress in the tendon is zero at the force end. Okay, at this point. Okay, the stress in the tendon is zero at the force end and is at a maximum value, and it is at a maximum value at some distance. Okay, at some distance from the end of the member. From the end of the member. This length is called as transmission length. This length is called as transmission length. Let me and it is denoted by LT. Transmission length. Okay. So within this transmission length, no, within this transmission length, there is gradual when the tendon is stretched and released. What happens? Again, there will be the tendon will get the different shape. Okay, let me write that shape in the separate diagram. Like this. Okay, like this, it will regain the shape tendon. Okay, I hope you are understanding. D1 is the original diameter of the tendon, and in the next step, it will be stretched to some required pre-stressing force. Okay, or some required length. Then after that, it is released. When the tendon is released, at the force end, at this end, the stresses will be zero, and the stresses will be having some maximum value at some particular zone here. Okay, this length is called as LT, that is transmission length. Okay, as the stresses is zero here, okay, the tendon will regain its almost original diameter. Okay, at the end. As the stresses goes on increases with the length, then the diameter also goes on decreases. I hope you are understanding. When it is stretched and released, at the end there will be zero stress. Because of zero stress, original diameter will be there as it is. Original diameter will be there as it is. Okay. With the length of the tendon, stresses, the longitudinal stresses goes on increases. As the longitudinal stresses goes on increases, the diameter will also goes on decreases. Goes on decreases. Okay. So which result in wedge shape over this length. Okay. This shape, it's look like a wedge shape. Correct? Wedge shape. So tendon will get the wedge shape at this particular length. This length is called as transmission length. This length is called as transmission length, and it is determined by using the formula LT is equal to root of FCU into 10 power 3 divided by beta. Okay, where FCU is equal to cube strength of concrete at transfer. Concrete at transfer. Okay, and beta is constant. Using this formula, we will find the transmission length. Okay, I hope you understood the concept of this transmission length. Okay, so to this theory part of this model is over. Let us go with the problems now. Okay. Okay. This is number is has to be changed. So it's the problem number one. This one. The problems are very simple and easy. You can do it. Very simple procedure is that you need to follow. Just go through this problem. A Frasinet anchorage 100 diameter carrying 12 wires of 7 dia is embedded concentrically in the web of an I section of web thickness 225 Using IS code method, determine the tensile and bursting tensile force in the end block. It is asked to find tensile force and bursting tensile force of the end block. Okay. So we already know the formula for finding this bursting tensile force and the tensile stress in the end block. Just before I told you the formula which are used for finding bursting force using this FBST formula, and by using this FE formula we find bursting force and the bursting stress. And it is also asked to find it is also asked to design the end block and to sketch the reinforcement details. Okay. Now let me write the diagram for the problem given solution. He says that it is an I section. Okay, it is an I section. Let me write the diagram of a I section. Okay. A Frasinet anchorage 100 dia carrying 12 wires of 7 dia. 7 dia is embedded concentrically in the web of I section. Okay. So it is a Frasinet cable. It is a Frasinet cable having a dia of 100 Dia is 100 100 carrying 12 wires of 7 diameter. Okay, there are 12 wires inside this Frasinet cable. Okay, there are 12 wires of 7 diameter inside this Frasinet cable. Okay, and this cable is Frasinet cable is placed concentrically. Concentrically means along the central axis. At central axis, it is placed. In the web of I section of web thickness 225 thickness of web is given 225 225 is the thickness of web. Okay. Using IS code method, determine the tensile and bursting tensile force. Okay. FV is asked, bursting tensile force. FBSD is asked to find, and design of end block is to be performed. Design of end block is to be performed. Okay. Now, to find this FBST, let us see what are the data required. For finding this FBST, we need the pre-stressing force. PK is nothing but pre-stressing force only. Don't get confused with the subscript K. Okay, it is nothing but pre-stressing force only. We need pre-stressing force. Okay. Then we need YP naught and we need Y naught. Correct? We need YP naught and Y naught. Okay. Therefore, first we will find this pre-stressing force. How to find this pre-stressing force? You find total area of the cable. Area of the cable multiplied by stress in the cable will give pre-stressing force. Correct? First you find the area of cable. Area of cable is equal to, so there are, the diameter of the cable are 7 mm. Therefore, area of one bar is pi d square by 4, pi into 7 square by 4 will give area of one cable. And there are 12 such cables which are placed in Flashnet cables. This will give total area of the cable. Okay. If you got the answer, you get it as 461.81 mm square. This is area of cable. And stress in the cable is not given, correct? In this problem, stress in the cable is not given. If it is not given, you take characteristic strength of the cable only. Okay, that is why we will assume characteristic strength FP is how much? It is a standard value 1600 Newton per mm square. In case of absence of data, we will assume it as 1600 Newton per mm square. Okay, this stress multiplied by cross-sectional area will give pre-stressing force, correct? Therefore, the pre-stressing force is equal to, if stresses in the cable is given, then you would have multiplied the stresses with this area of the cable. If it is not given, you will take this FP value only. That is 1600 Newton per mm square is equal to P is equal to stress multiplied by cross-sectional area. Stress is 1600 multiplied by 461.81. Therefore, P is equal to, we will get it as 738.896 into 10 power 3. Okay. Now you got pre-stressing force. Then you need to find the size of the prism. You need to find size of the prism, means this 2y0. 2y0 value is required. Size of the prism. Okay. To find this size of the prism, as I said, we need to calculate in two ways. One is equal to 2y1. One is equal to width of the beam. And it is BW in case of T beam or I beam, width of web. It is given in the problem. Okay. Write the side as size of prism A. Size of prism. Size of prism. The first calculation is what? First calculation is 2y0 is equal to 2y1. 2y0 is equal to 2y1. Okay. Where y1 is, as I said, it is nothing but distance of nearest extreme fiber from the tendon. This y1 is not given in the problem. Okay. Then if it is not given, then leave it. Okay, in the bracket you can write y1 is not given. And we have one more calculation, that is 2y0 is equal to, what is that? Width of beam and BW. Width of beam, width of beam. Okay. If this is a I section, for I section or T section, we need to take this width of beam as width of web is equal to BW is equal to, it is given as how much? 225 mm. 225 mm. Okay. We need to take least value of these two calculations. Out of these two calculations, we need to consider least value for 2y0. So here we have only one calculation. Whatever the value we got from this second calculation, no, that only we'll consider it as size of the prism. Therefore, 2y0 value size of the prism is equal to 225 mm. Okay. Now you got this size of the prism 2y0 value. How much you got? 225 mm. Okay. Then next step, the area of the prism. Find area of the prism equal to 2y0 into 2y0 is equal to 225 into 225. This will give area of the prism AP. Okay, area of the prism AP. Okay, if you know the pre-stressing force and if you know the AP value, then you can calculate compressive stress FC. Correct? You can easily calculate compressive stress FC. FC is equal to P by AP. Okay. Therefore, the compressive stress stress compressive stress is equal to FC is equal to P by AP. Okay. So P force P is calculated 738.896 into 10 power 3 into 10 power 3 divided by area of prism is 225 by 225. By this you'll get the compressive stress value, that you get it as 14.59 Newton per mm square. Okay. So in this first step, what we have calculated, we have calculated the size of the prism, and by knowing the size of the prism, you have calculated the area of prism AP. Okay. Knowing the area of prism and pre-stressing force, we can calculate the compressive force in that prism, that is P by AP. That we got it as 14.59 Newton per mm square. Okay. Now in the second step, what we'll do is, here the Frasinet cable is having the circular cross section, correct? Okay. Frasinet cable is having circular cross section. As I explained in the introductory class, if circular section is given, we need to find an equivalent square section. So in this step, we will find the equivalent size of anchor plate. We will find equivalent size of the anchor plate. Okay. And diameter of the Frasinet cable is given as 100 mm. Let me write the diagram here. Continue the class. So we'll find an equivalent size of a square plate. Okay. Okay, diameter is given as diameter of the fluorescent cable is given as 100 mm. 100 mm. Okay. So we'll find the equivalent size of a square plate. Okay. Therefore, we have to equate the area of plate to that of area of the circular cable. Correct. Therefore, a square is equal to a into a will give area of the square plate, and pi d square by 4 will give area of the circle. Okay. Therefore, a square is equal to pi into d is 100 square by 4. Okay. Therefore, a if you solve, we'll get the answer as 88.62 millimeter. 88.62 millimeter. Okay. Now, what you have done is you have converted the area, the circular cross section into a rectangular section, which is directly equal to 2 yp naught value. The size of the plate, the depth of the plate. Here I explained no 2 yp naught. Okay, the square plate size depth is taken as 2 yp naught. Okay, now you got the value of 2 yp naught, that is 88.62 millimeter. 88.62 millimeter. Okay, so this is the second step. This step will be there only if circular cross section is given. If it is rectangular section is given, this step will not come into picture. Okay, C. Okay, finding the tensile stress. Tensile stress. Okay, so we know the formula for finding the tensile stress. Here we have the formula. Let me copy this formula. We know that FV max is equal to FC into 0.98 minus 0.825 into yp naught by y naught. Okay, so FC is calculated compressive stress. How much it is? 14.59. 14.59 into 0.98 minus 0.98 minus 0.825 into yp naught by y naught. Okay, yp naught by y naught means here 2 yp naught is equal to 88.62. half of it will be 44 something. And y naught, here we have 2 y naught value, that's 225. Half of it will be some value. Instead of dividing it by 2, whatever the values are there, 225 and 88.6, directly substitute, you will get the same answer. Yp naught by y naught is 225. 225. See, if you want, we can divide by 2 and substitute here. Even if you substitute directly, you will get the same answer only. Okay, that is why I am substituting directly. Okay. Both are on same calculations only. See, finally you will get the same answer only from both the calculations. Fe is equal to, if you calculate the answer, the tensile stress that you get is 9.55 Newton per mm square. 9.55 Newton per mm square. Okay. So to this we got that's it, the tensile stress. Then what next? Bursting force that we can find now. Next step. Next step is bursting force D. Bursting force we have the formula in the code book. Let me copy this same formula. This formula is available. FBST PK is equal to 0.32 minus 0.3 Yp naught by Y naught. FBST by PK is equal to 0.32 minus 0.3 Yp naught divided by Y naught. Available in page number 36. Okay. Therefore, the FBST value will be equal to PK into 0.32 minus 0.3 Yp naught divided by Y naught. Therefore, processing force P is down. How much we got? Nothing but PK only. Don't get confused. Both are same only. 738.896 into 10 power 3. 738.896 into 10 power 3 into 0.32 minus 0.3 Yp naught by Y naught. Same ratio. I will substitute 88.62 divided by 225. By this we'll get bursting force FBST as 149.13 into 10 power 3 Newton. Okay. So in the question it is also asked to design the end block. We'll design the end block as well now. Design the end block. Design of end blocks. Write the headline as step E. Design of end block. Design of end block. Okay. So if you know the bursting force, you can calculate the area of steel required. We have the formula here. Remember this formula, FBST by 0.87. Area of steel is equal to AST is equal to FBST divided by 0.87 Fy. Okay. Assuming the mild steel. Okay. For mild steel, Fy is how much? 250 MPa or 250 Newton per mm square. Therefore, AST is equal to FBST value is 149.13 to 10 power 3. 149.13 into 10 power 3 divided by 0.87 into Fi, that is 250. By this we will get area of steel. We will get the area of steel as 685.7 mm square. 685.7 mm square. Okay. Now you got total area of steel required for end block. Okay. Now decide the diameter of the bar to be provided. Now I'll assume, okay, are using 10 mm dia bars. You can find the number of bars now. How will find the number of bars? Number of bars will be total area of steel. Total area of steel required divided by area of one bar. Area of one bar. Okay. Total area of steel required is 685.7. We have assumed a 10 mm diameter bar. Therefore, area of one bar will be pi into 10 square by 4. By this, you will get the answer as 8.73. Okay. You can roll it off to 9 numbers. 9 number of bars in both direction, in horizontal as well as vertical direction. In each, a very simple design. Okay, finally, you need to write the reinforcement details at the end block. Okay, write the longitudinal section of the beam. This is one end of the beam. It is simply supported always. Okay, so we'll leave some cover here. Okay, this length should be how much? Is 0.2 y naught. Okay, after this we need to start providing this the end block reinforcement. Okay, now okay, this length will be y naught. Okay, to y naught, and the bar should be provided in both directions, both horizontal and vertical direction. Okay, so this is the longitudinal section. If you write the cross section, no, cross section of this end block, what you will get? You will be able to see a steel mesh. Like this. Okay. So here this is 9 numbers of 10 mm dia in both directions. Both the bars. Okay. Okay, it is like a steel mesh. Okay, we have to provide that mesh. Total 9 numbers. Okay, so this completes the problem. If you got any doubts at any point of calculation, you can ask students. Any doubts here in this problem, students? Any doubts you can ask? Thank you. Now we'll move on to the next problem. Problem number 2. Problem number 2. Go through it. The end block of PSC beam, rectangular in section, 150 mm wide and 400 mm deep. An effective pre-stressing force of 400 kN is transmitted to concrete by a distribution plate of 150 mm wide by 120 mm deep, concentrically located at the ends. Let me write the diagram for this. It is a rectangular beam. Solution. The rectangular beam. It's a rectangular beam having dimensions 150 and 400. 50 and 400. Okay. An effective force of 400 kilonewton is transmitted. Force P is directly given. Okay. P is equal to 400 kilonewton, nothing but 400 into 10 power 3 Newton, which is denoted by PK in this fifth model. Okay, nothing but PK only. Then transmitted for an effective pre-stressing force of 400 kilonewton is transmitted to the concrete by a distribution plate of 150 mm wide by 120 mm deep, concentrically located at the ends. Concentrically located means, let me write the central axis first. Central axis, and that plate having dimensions of 150 mm wide and 120 mm deep. 150 mm wide means it is equal to width of the beam only. Okay. And depth of the plate is which is nothing but YP naught only. Okay. 2 YP naught is equal to how much it is given? 120 mm. It is directly given. Okay. Calculate the reinforcement for the end block for maximum transverse tension. Sketch the details of reinforcement. We have to design the end block, that's it. We have to design the end block. Okay. Now in this case we can find Y1. Correct? Y1 is what? Y1 is nothing but distance of nearest fiber from the center of the pre-stressing force. Y1 is equal to 200 divided by means 400 divided by 2. Y1 is equal to 400 divided by 2, 200 mm. So in the previous problem, that Y1 was not given. Okay. Y1 was not given. Overall depth of the beam was not given. Okay. If overall depth is given, you would have got this Y1 value. Okay. That Y1 is calculated is required for fixing the size of the prism. Okay. So in this problem, overall depth of the rectangular beam is given. That is why we got Y1 here. Okay. Now we have to design the end block. Okay. The size of the anchor plate, it is known only. Size of anchor plate So in this we need 2 YP naught value, correct? Which means the depth of the plate, which is equal to 120 mm. 120 mm. Okay. Then size of the prism, we will fix the size of prism. See, very simple concept, friends. Initially, you need to find these basic things. Okay, basic things like sometimes pre-stressing force will be directly given. Force, pre-stressing force. Okay, and you need to find this 2 y naught value and 2 yp naught value. Then compressive stress P by AP value. Okay. If you know all these three things, FC and YP naught and Y naught, then just by substituting the values, you will get the required tensile stress, bursting force, and you can easily design the end block ESD as well. Okay. Only the thing is you need to find FC, YP naught, and Y naught. That's it. Okay. Now we got YP naught value, 2 YP naught value, size of the prism. So we have the guidelines as guidelines here. It is we have to calculate 2 y naught values by using two different calculations. 2 y naught is equal to 2 y1. First calculation. 2 y naught is equal to 2 y1. So y1 value is known in this case. Y1 is equal to how much? 200 mm. 2 into 200. 400 mm. 400 mm. Then one more calculation is there. What is that one more calculation? Width of beam. Width of beam. Okay. Width of beam. Width of beam is how much? 150 mm. 150 mm. So out of these two calculations, we need to consider least value as 2 y naught. That is size of the prism. Which is the least value? This one is the least value. Therefore, take 2 y naught is equal to 150 mm. Okay. So in this problem, it is not asked to find this tensile stresses. It is directly told to design the end block. Okay. No need to find tensile stresses now, as we determined for the previous problem. In the previous problem, it was asked to find the tensile stresses. We have found it. Okay. We can skip this step now. Okay. It is not asked in this particular problem. Okay. We need bursting force for design of the end block. Therefore, you find the bursting force in the next step. Okay. Bursting force. Bursting force. We have the formula. FBSD is equal to EK is equal to 0.32 minus 0.3 YP naught divided by Y naught, which is there in page number 36. Therefore, FBSD is equal to PK into 0.32 minus 0.3 YP naught divided by Y naught. Okay. Therefore, bursting force is equal to pre-stressing force is 400 into 10 power 3. 400 into 10 power 3 into 0.32 minus 0.3 YP naught divided by Y naught. Okay. Oh, 120 by 150. Okay. See here, YP naught value actually it will come around 60 mm. Here you will get 75. 60 by 75 is value is also same. 120 by 150 value is also same because 2 YP naught divided by 2 Y naught will give what? It will give YP naught by Y naught value. Therefore, I substituted directly 120 by 150 instead of making it half and substituting. Okay. I hope you don't have any confusion in this substitution. ABC ST is equal to bursting force is equal to, if you calculate, you will get the answer as 32,000 Newton. 32,000 Newton. Okay. Now we can design the end block. Last step, design of end block. D. Design of end block. Okay, same steps here. Find the area of steel. Area of steel is equal to, what is the formula? FBST divided by 0.87 FY. FBST is 3 and FY it is, here it changes. No problem. Change this to FE 250 because if you assume FE 415 value, no, you'll get you will not get at least 2 bars. Okay, because here the bursting force is lesser. Okay, you can perform using this FE 415 also. Change it to 250 grade of steel. 0. What is this? 32,000 divided by 0.87 into FY 250. Okay, by this you'll get area of steel. You'll get it as 147.12 mm square. Okay. So if you assume 450 now, still you will get lesser area. Still you will get lesser area. You will not be able to provide at least 2 bars. That is why. That is why I changed the FI value to 250 here. Okay. So in the examination, if they give 415, you assume 415 only. Whatever the number of bars you will get, you put the same number of bars. No problem. Okay. Here, as the area of steel is lesser, I'll assume lesser diameter of the bars. Assuming 6 mm dia bars, you can calculate the number of bars. Number of bars is equal to area of steel, total area of steel divided by area of 1 bar is equal to 147.12 divided by area of 1 bar, pi d square by 4, pi into 6 square by 4. Okay, so you get the answer as 5.2. You can round it out to 6 numbers in each junction. Okay, so writing the reinforcement details is similar to that of whatever we have written in the previous problem. Same way you need to write the reinforcement detail. Leave some cover here. So this is the prism area or area of the end block. That is 2 y naught. How much you got? 2 why not? 150 mm. Okay. Write the reinforcement details. You can also write the cross section. Okay. Mm. Okay. So this completes the second problem. Any doubts you can ask? Okay, students, to this, I'll end the class and I'll continue in the tomorrow's class. Thank you.